Well, good morning, everybody. Sorry that we're starting just a couple of minutes late. I was making some last-minute changes to the lecture slides and things, and so I just needed an extra couple of minutes to upload things. So, hope we all had a good weekend, and it's nice that people are saying hi in the chat. Do say hi to each other, and hopefully we can continue to build that sort of sense of class camaraderie. That would be very nice. Let me start off today. Yeah, there we go. Lots of highs coming by. That's fantastic. Let me start out the day by asking you a little top hat question. See how we do with this. So there is an error here. Where is it? So while people are starting to answer that question, what else do I need to say? So assignment 1 and assignment 2, hopefully everyone's had a chance to finish off assignment 2. As I mentioned, there was an opportunity if you were someone who, like your assignment 1, the problem was that you didn't have the exact right prompt that you passed to the input function. Then I gave people a second chance to just send me an email with your updated version, and at least one student took advantage of that, so that's great. Assignment 2, apart from like someone who had a particular reason to have an extension, I think we're mostly done with assignment 2 now. So I've posted all those grades to Brightspace, so you can see how you're doing in terms of assignment grades and lab marks, at least those that you have back so far, etc. And hopefully that is helpful for everyone. Someone says the pre-lab for lab 5 is a little confusing. Would you be able to go over it? I will see how the time goes. I don't think we'll have time during this particular slot. However, I'll take a look at it and see if maybe there's an opportunity to go over it in some way, or possibly even if you have specific questions, you can send them and we might be able to answer them, post something to the course website. Maybe even if there's something confusing, we might clarify something. So we'll try to do something for you, but it may not happen during this 11 to 11:50 slot. But we'll definitely try to do something. Something else I'd say, this Wednesday, it looks like I'm going to have something I don't get very much of this semester. I'm going to have 2 separate hour-long slots back to back in which I don't have lectures or meetings or things like that. This is pretty unusual for a winter semester. So what I think I'm going to do, obviously I'm going to fill it. However, I think some folks are at the point now in the semester where maybe things are really kind of becoming real, as it were. And so I'm thinking I'm going to have a couple of extra office hours on Wednesday. So between 12 o'clock and 2 o'clock, my intention is to kind of mostly stick around my office. I mean, I may pop out for 10 minutes to get coffee or something, but I will mostly try to be around my office between 12 and 2, so that if you have questions or if you want to chat about like, here's where I am and I'm feeling kind of desperate because, this was my midterm mark and how can I get back on track, etc. So whether it's specific questions or broader questions, I'm going to try to be around so people can answer, so that I can chat with you then. All right, so we've got some answers coming in, so I'm going to go ahead and close this. And let's see if people were able to find the right place. And yeah, there we go. So most people did indeed spot the correct error. That's a funny thing to say. The issue here is that we have these default arguments, and you can't have you can't have arguments without default values after. You can't have parameters without default arguments after you have parameters that do have default arguments. Just like you can't have in a function call positional arguments after keyword arguments. And the reason for that is because this could introduce confusion, right? So if somebody calls foo here, and if we were allowed to have a default argument for x and a default argument for y, and no default argument for z. So if somebody calls the foo function and passes in the numbers 10 and 20, well, which parameters are those arguments supposed to go into? So that could be very confusing. And so that behavior is just not allowed. And most people saw that that was indeed the case. So that is great. Let me ask you something else here that's, again, kind of like a reviewing ideas from last time. So step through this and see if you can figure out what the value of z will be when the script is done running. So this will take just a minute for people to walk through, and that's fine. Some answers are starting to come in, so that's great. All right, I'll give us maybe just a few more seconds on this one, maybe another 10 or so. And if you aren't able to get this question now, then certainly I will open it up for homework so that you can do it afterwards. So that's going to be another 5, 4, 3, 2, 1, and close it. All right, let's take a look at the answers that people gave. All right, so mostly we had the number 56. Now, how did we get that? So let's try popping open Thonny. And look, I actually remembered to open it. Hooray. So if we define this function called foo, and foo returns x plus 2, y is foo of 42, and z is equal to foo of foo of foo of foo of foo of foo of y. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Yep, that's right. Okay, so let's step through this program one step at a time. So first we're going to define that function. Then we're going to call the foo function. So we take 42, and 42 is what? Let me restart that from the beginning. Is 42 here an argument or a parameter? Argument or parameter? What is 42? All right, people are typing, and that's right. This is indeed an argument. So we're going to take that argument, 42, pass it into the foo function, and now we have that parameter x has been filled up with the value 42. So we're going to compute what is x plus 2. Well, that's 42 plus 2, so that's 44. We return 44, which means this function call evaluates to 44. So y is 44. Now, what are we going to do? Well, we are going to call foo of foo of foo of foo of foo of foo of y. So what's the order of operations? Well, we do function calls before we do other operations, like if you had foo of y plus 2, well, first you figure out what is foo of y, then you can add it to 2. So what is foo of y? Well, what is the value of y? Y is, if we look at the variables window, y is whatever it says in the box, whatever value is currently held in memory. And so that is 44. So we're going to take that number 44, and we're going to pass it to the foo function. So we're going to call foo with the value of 44 passed in for x. And then we're going to compute what is x plus 2. So that's going to give us 46. So we return 46, and then 46 gets passed into the next foo, which is going to give us 48. Then 48 gets passed into the next foo, which is going to give us 50. Then 50 gets passed into the next foo, which is going to give 52, and then 52 is passed into the next one, etc. 54, and then finally we pass 54 into the foo function. And so every time we've called foo, there's a different local variable called x. So this calls x, and this calls x. They have different variables, different places in memory potentially, and they can have different values. So this time 54 gets passed into x. 54 plus 2 is 56. And so that returns 56, which means that z takes the value 56. And it looks like most people did indeed have the right answer there. So that's good. Now, I left you with this question. I asked you, what is wrong with this function as it is currently described? What's wrong with this definition of the factorial function? And so hopefully everyone had a chance to kind of walk through this, and I said, well, let's take the factorial of, 5, for example. Sorry, not sick, just throat is a little bit dry this morning. Let me see if I got some water in this kettle. I do. The lecture is saved. All right, so I said there is something wrong with this definition of factorial. And I suggested that you try to walk through, well, for example, what is the factorial of 5? Well, we're going to define this factorial function, then we're going to call it. Take the value of 5 as an argument, pass it into factorial, and so this parameter n gets the value 5. So what is the factorial of 5? Well, it's 5 times the factorial of n minus 1, which is 4. So it's 5 times the factorial of 4. Well, what's the factorial of 4? Well, it is 4 times the factorial of 3. And so we take the value 3 and pass it to the factorial function. And what's factorial of 3? Well, it's 3 times the factorial of 2, which is 2 times the factorial of 1, which is 1 times the factorial of 0. So we're going to take the argument 0 and pass it into the factorial function, and then the factorial function will have a parameter n with the value 0. And notice we've got all these different factorial function calls that are kind of going on at the same time, because factorial of 5 is waiting for the factorial of 4, which is waiting for the factorial of 3, which is waiting for the factorial of 2, etc. So, and these functions kind of stack up. In fact, we call this a call stack, when one function calls another one, which calls another one, which calls another one. If you were to just list all of the functions that are calling each other at this moment, we call that a thing called a call stack, because they kind of stack up. And because they use a region of memory called the stack. But that's maybe something that's more for like EC 3400. But now we're going to compute the factorial of 0. What is the factorial of 0? What should the factorial of 0 be? Yeah, it ought to be 1. But what are we going to compute here? We're going to... If we use this definition that we have, it's worked so far, right? Factorial of 5 is 5 times the factorial of 4. Factorial of 4 is the factorial of 4 times, or is 4 times the factorial of 3. This definition, this recursive definition, has worked for us thus far, but now we hit a problem, which is that now we're going to compute the factorial of 0 as 0 times the factorial of n minus 1. So 0 times the factorial of negative 1. And the factorial of negative 1 is negative 1 times factorial of negative 2. And negative 2 is the negative 2 times factorial of negative 3. Uh-oh, we've got a problem here. So what is fundamentally the problem here? Well, the problem is that this factorial, this definition of the factorial, is incomplete. It is missing something. And in particular, this is going to go on forever. We will then figure out what is factorial of minus 3, minus 4, minus 5, minus 6, minus 7, minus 8. And never stop. So just like when we use a, just like when we have a loop that we use to compute a value, we need to be aware of an infinite loop. Well, similarly, when we're thinking about recursion, we need to be aware of an infinite recursion, which means that whenever we do whenever we do recursion, we need to be thinking about, okay, what is the common case? How can we define this step in the calculation in terms of the same calculation for a different value? So we can say factorial of 5 is defined by 5 times whatever the factorial of 4 is. So that's great. That recursive step, we've got that down. But just like in a loop, we think through what is the common case first, what is the thing we do every time through the loop, and then we have to think about things like, well, how do we start and how do we stop, and when do we know to stop? Similarly, whenever we think about recursion, we need a base case, which is, when do we stop this recursion? So in the case of factorial, the base case would be if n is equal to 0, we return 1. Otherwise, we can use that recursive step. So if I calculated the factorial of 10, then we would compute the factorial of 10 is 10 times factorial of 9, which is 9 times factorial of 8, which is 8 times factorial of 7, etc., all the way down until we get to 0. And the factorial of 0 is 1. So now when we run this, and I'll step through it like super fast, not as fast as the computer would if we weren't doing the step thing, but we'll step through this as kind of quickly as we can. And isn't it nice how Thonny opens up a little separate window for each call so we can really see what's going on? This is why Thonny is so nice for teaching purposes. It's not really a super duper IDE for general programming, but for teaching purposes, it's great. And so now we check if n is equal to 0, well, then we're just going to return 1, which means then we start stepping back out. So the factorial of 1 is 1 times 1. We return 1. Then the factorial of 2 is 2 times 1, which is 2. So we return 2. The factorial of 3 is 3 times 2. So we return that, etc. Until we finally get to the factorial of 5 is 120, which is correct. So, all right, good. Hopefully that, yes, and that was the last thing that we didn't quite get to. So just like when we're thinking about a loop, we have to think about when do we stop? Well, when we're thinking about recursion, we need to think about when do we stop. And so whenever we write a recursive function, we're going to think about what's the recursive step, what's the way in which we do a little bit of work now, and then ask the same function to do the next step, or working from the outside in, what's the next layer of the onion, as it were. But we also need to think about what's the base case. When do we know that we're done? When do we know that the recursion needs to stop? Okay, so that was the end of some more things about functions, including recursion. Any last questions about that before we start talking about today's topic? Okay, no questions, so let's carry on. So now that we've got a bunch of different tools to put in our little programming toolbox, and so we can solve problems that involve primitive values like numbers and like Boolean values and strings. Now we can also solve problems that involve collections of values, whether they be lists or strings of characters. We can solve problems that involve iteration, loops, and now we've got functions as a tool for describing new abstract procedures that we can use within other procedures. So we've got lots of tools here. So we can write lots of code, and we can write code of increasing levels of complexity. And so now we have to ask, well, how do we know when our code is right? Or how do we know when our code isn't right? What is correctness anyway? And how can we check to see if our code is in fact correct? So what is correctness? And from a software perspective, software is correct when it always, 100% without exception, always does the right thing. Now, how do we define the right thing? That's something that we're going to come back to a little bit later in this lecture. So no mistakes at all. So in ordinary circumstances, if you're not talking about software, but if you're talking about, for example, people doing some work, then, if you make a mistake once every million students you process their records for, or if you make a mistake one time in every million cars you create or something. I mean, that doesn't seem so bad, right? It doesn't, one in a million. That's not very frequent. Well, the problem is that computer processors execute billions of instructions every second. And so we really don't want to make a 1 in a million mistake, because that could potentially lead to thousands of errors per second. So the sheer speed at which software executes means we really need to have a high standard of correctness if we're going to have things work like at all. I said here, how about a 1 in a 9 billion mistake? The link there, if you want to click that later, is to a problem that was discovered in an Intel CPU called the Pentium way back in the day, in which there was a very particular kind of floating point calculation that it would get wrong. And it was a very infrequent kind of thing. Like this number was not, or this division was not a division that happened to be done very commonly. But still, Intel ended up having to recall every Pentium chip they had ever sold at that point. Now, some people hung on to them because they knew these would become like really rare collector's items, that kind of thing. But that was an instance in which even something really infrequent was extremely expensive for them, but also very damaging for their reputation. And after that, formal methods for proving the correctness of CPU designs became a really important topic in research. So how can we check whether things are correct? So ultimately, what would be really nice would be if we could use mathematical proof. So if we could prove the correctness of our software, then that would be great, because, well, if you prove something correct, then I guess it's correct. And in some circumstances, that is possible for limited circumstances, for relatively small pieces of code that do extremely specific things, where it is possible to specify their behavior very tightly. It is possible in some circumstances to prove that your code is in fact correct. But in practice, this can be really difficult. So I have a picture here of a system called Cell 4, which is like a really low level mini kind of micro operating system. Well, it's actually called a microkernel that runs underneath a lot of other stuff in, for example, phones and other stuff. In parts of your phone where there are extremely high requirements for satisfying regulators that your phone isn't going to fool up all the other phones in a cell and that kind of thing. And even some really high assurance systems like Cell 4, there are mathematical proofs of correctness that exist, but as the authors say, I quite like what they kind of remind us of, which is that when you have a mathematical proof of correctness, it proves exactly what you have stated, which is not necessarily what you mean or even what you want. So it is possible to prove that this piece of software, under certain assumptions, when you assume the hardware is perfect and when you assume this assembly code isn't invalid, and when you assume certain other things and make lots of assumptions, it's possible to prove that this little piece of code conforms to these mathematical axioms. But then you have to ask yourself, are those mathematical axioms the right ones? Do they actually describe the real world behavior we want? So proving software correct is a very worthwhile activity, and research continues. People continue to push the boundaries of how much stuff we can prove correct. But most code can't be proven correct. There's an active area of research, but most code cannot be proven correct for two reasons. One reason could be that your code is beyond the size or the complexity that we're able to prove things about, because we can only prove things about kind of smaller bits of code. That's one possible reason. Can anyone think of another reason why you might not be able to prove that your code is correct? Any other reasons at all why you might not be able to prove that your code is correct? Yeah, maybe your code isn't correct. That's right. That could be the other reason. So if proving correctness is kind of too difficult and in a lot of circumstances impractical, well, what's the next best thing? And what we are left with is testing. And so in testing, there are really kind of three different things that we need to think about, three different artifacts that relate to testing that need to kind of work together. And that is code, specification, and test. So you have code, you have specifications, and you have tests. And you see from our little diagram here that, oh, actually I should put my face away for a sec so you can see the whole diagram. So code ought to implement a specification. So really the thing that we care about the most is that the code does whatever it is that we want it to do. The trouble is that what we want is kind of a nebulous idea of what is it that we actually want the code to do. And it's hard to describe that in such a way that two people can even agree on whether the code is behaving correctly. So the code should do what we want, but what we actually do in practice in order to facilitate testing is we make sure that there is a specification that describes what we want as closely as possible. Then we write the code to implement that specification. Then how do we know if it actually does the right thing? How do we know if it faithfully implements the specification? Well, we could prove it mathematically if that were possible, for if you have a problem that is small enough and in some circumstances, you can prove that, but in a lot of circumstances, instead, what we have to have are tests. So we write tests that are based on the specification, and then the tests check the behavior of our code. So what does that mean in practical terms? So you've worked really hard on writing lots of code, and hopefully that code is correct. Hopefully it does the thing that we want, but how can we possibly really tell? This is something that I've mentioned has come up a few times in even back and forth about assignments and things, where a student will submit something to Gradescope. So assignment code goes to Gradescope, and Gradescope runs a bunch of tests that I've written. And then you might say things like, well, it works on my computer, or it works perfectly fine for me. But then we need to debate, what does perfectly fine mean? If it doesn't pass the tests, does it really work perfectly fine? It's kind of like when someone says, well, it works for me. In software, that doesn't work very well, and in other circumstances, that doesn't work very well. So I've got I'm sorry, I don't have the PDF version of the notes from today's lecture uploaded yet, but I will. And you will see in the PDF version of the notes, you'll see things like a little story in which I talk about how my previous car, so not our current car, but the last one, the air conditioning didn't work. How do I know it didn't work? Because when we would go for a long drive on a hot day, it would be really, really hot. And, we don't really want to have the windows down on the Trans-Canada all the way to Deer Lake to see Nan and Pop, but on the other hand, it was really, really hot inside the car. But then I take the car to the shop and they turn it on and say, well, air conditioning works for me. Look, I put my doohickey on this hose and it says that everything is fine. So we would have this fundamental disagreement about, does the air conditioning work or not? And you'd think that would be something that would be really, really easy to tell. Is this a true statement or is this a false statement? The air conditioning isn't working. But it turns out that even something that simple, there can be disagreement as to whether or not the thing works. Anyway, I turned it back into, when we got our new car, we turned it into the garage. And so if they didn't believe me that the air conditioning works, well, it's their problem to figure out now. All right, so we have the code that we have worked on that we would like to believe that is correct, but how do we know? So we are going to write someone is going to write a specification, which is a precise description of what is supposed to happen. When I release an assignment, and I do owe you an assignment 3, I should release one very soon, maybe tonight, hopefully, we'll see. When I give you an assignment page, that is a specification of what your code is supposed to do. It says, here's the overall objective. Now, here are some details. When you do this, you need to print out exactly this string. When I give this input, you ought to give exactly that output. So it ought to be a precise description of requirements. And some students have already discovered that in some cases, the specification is silent on certain things. So they said, well, for example, if somebody guesses a 6-letter word in the Wordle game, does that count as a guess or does it not count as a guess? And I see that the specification actually missed that detail. It didn't say, which means that I can't hold you either way. So you could do it this way or you could do it that way, and either one conforms to the specification because the specification was missing that detail. And that's a good example of how a specification can never capture all of the behavior that we want. It tries to, and we try to capture as much behavior as we can, and it attempts to capture all of the required behavior, but sometimes specifications miss things and can need improvement. There's a question. Are we going to complete all 6 assignments before classes end on the 8th? Yes, that is definitely the intention, and that's why I need to get assignment 3 out to you pronto, if there's going to be time for that. So a specification is a model of what we want. It's not actually our intuitive sense of right and wrong. It is a model of what code ought to do, and that specification ought to correspond with the real world. So if we're going to have a specification that describes here are the concrete, specific, precise requirements for your code, we would like it if that specification had something to do with the real world. It is easy to test whether or not code conforms to a spec. Then the question is, does the spec actually say something useful? So mathematical models are precise, they are reproducible, and that is super helpful. But if they don't correspond to the real world, well, that's not very useful in the broader sense. And if you're ever wondering who would ever write a specification that doesn't conform to a real world expectation, then you should talk to the staff in the ECE office on the first floor who are wearing winter coats in the office, because although the heating, ventilation, and air conditioning do live up to the required mechanical specification, apparently that specification didn't take Newfoundland winters into account or something, and so they're freezing down there, even though it technically lives up to the specification, which means there's a problem with the specification, which means whoever came up with that specification probably has some work to do. So we have code, we have a specification, and then we have tests. So a test is an input or set of inputs and an expected output or set of expected outputs. So based on the specification, independently of looking at your code or your code or your code, whoever writes the test ought to look at the specification and say, all right, the spec says that if you put this input into the code, then you ought to get this output from the code. And this is something that you can check independently against the specification. So we don't check our tests against people's code. Well, it passed against this person's code and it didn't, or this person's code passed the test and that person's code didn't pass the test, so I guess that's good. No, we can verify. And if, for example, you look at your assignment results on assignment 3, 4, 5, or 6, and you say, test number 3, I'm not sure about that. Well, if you're not sure about that, then we're not going to look at the correspondence between your test and the code. We're going to look at the correspondence between your test and the specification and say, okay, forget your code for a second. Is the test right? The test says that if I put the input 1, 2, 3 into this function, I should get the output 4. Is that what the specification says? And we go look at the spec and say, yep, if you were to put 1, 2, 3 in, then the description of the behavior that you're supposed to get, you should output 4. So we can check the test against the specification, and then we can check the code against the test. So again, if all was like, if we were living in a dream world and if all was ideal, then we would be able to mathematically prove that the code implements the specification. But in a whole lot of cases, we really can't do that. So what we do the next best thing, which is we try to write tests that are based on the spec, and then we use the tests to check the behavior of our code. Let's think about, okay, first, any questions before we carry on? No? All right. Well, very good. So let's think about the limitations of testing. Part of the reason why we would really like to be able to prove things mathematically is because if you can prove something with a proof, then the proof is done once and everything is settled once and for all. We don't need to. If I can prove that a certain algorithm calculates the factorial of something, then I don't need to check, well, how about the factorial of 5? Can it calculate the factorial of 10? Can it calculate the factorial of 2? I don't need to check all of these different possibilities. I just do one proof and then I'm done. And so it's very general, which is great. Sometimes we have to do testing though, but testing has limits. So just think about this question for a second. How long would it take to test 2 to the 64 possible inputs? So if I have a function that takes a number, and that is a 64-bit number, then there are 2 to the 64 different possible numbers that I could put into that function. So a Python float is usually a 64-bit IEEE double precision floating point number. So there's 2 to the 64 different possible values that I could pass in. How long would that take to test if I wanted to check every single one of them? Well, first of all, what is 2 to the 64? Somebody just type in the chat. What is 2 to the 64? It's a rather large number. All right, nobody seems to want to type it into the... Oh, no, someone is. Good. Yeah, there we go. So it's around 1.8 times 10 to the 19. So let's say, okay, that's fine. It's a big number, but, computers are really fast. Let's say I can test 1 million instances of this function per second. Well, 10 to the 19 is a big number, but I can test 10 to the 6 per second. Well, 10 to the 19 divided by 10 to the 6, we're still going to have to test, or it's still going to take 10 to the 12 seconds. So what would 10 to the 12 seconds be? How long would that be? So 10 to the 12, well, actually, you know what? Let's use Python as a calculator. So if we have 2 to the 64 divided by 1 million, right, that's still a pretty big number. How big is it? Well, if we can test that many, or if we need that many seconds, that is that many hours, which is that many days, which is that many years. So we would need 584,000 years to test a little Python function that takes a number in and outputs a number. That's not very practical, right? If you write one function, I don't want to spend 584,000 years testing your function, right? So generally speaking, except in very limited circumstances, we can never test exhaustively. That is to say, we can never check every single possible input. So if we're going to test something, and I would suggest that, especially now that we're getting to functions, it's going to get a lot easier for you to test your own code because and even to share test code. So assignment code has to be your own work. But if you write a function and everybody writes their own functions, maybe you could if everybody has to write the same function with the same name, you could share test code, which would be like, here's a script where if you paste your function in at the top, it'll check to see if it works. Sharing test code with each other would be great. Thinking about how should my function work and what should it do, thinking about things externally gives you a different perspective, which will really help you understand how your code is or isn't working correctly. So definitely would encourage you to think about writing your own tests and even sharing tests with each other. Don't share your assignment code, but share your tests with each other. That'd be super. If you were going to write code to test, for example, in this case, I've said, imagine that I tell you to write a function, and I'm not actually going to do this because I don't have the simple algebraic answers to these to hand, but let's say that somebody wrote a function that was going to figure out if you pass in a pressure and a temperature, it would tell you what phase of water you were going to get. So here is the phase diagram for water. So at 1 atmosphere of pressure, what we're used to, water goes from ice to water at 0 degrees, and it transitions between water and steam at 100 degrees, so solid, liquid, gas. But of course, at different pressures, those things happen differently. If you are on top of Mount Everest, water boils at a little bit less than 100 degrees because the air pressure is less than at sea level. And there is a place called the triple point where if the pressure is very, very low indeed, then water can boil or freeze or sublimate at 0.01 degrees Celsius, which is kind of cool. But let's say that you had a company and you were doing chemical simulations and you paid a software developer for their time to write a function that would just tell you, if I give you a pressure and a temperature, what phase should water be in at that point? How would you know if their code was right? Would you just sort of look at it and say, yeah, I don't see any mistakes, so I guess it's 100% correct? No, probably not. Would you prove it mathematically? No, you probably couldn't do that. So instead, you would write some tests. And if you had to choose what inputs of pressure and temperature to test, how would you pick them? So give me some examples from this diagram of pressure, comma, temperature pairs that you would use as inputs. Okay, so someone says test at 100 degrees Celsius. Yeah. Okay, 100 degrees Celsius and what pressure? Okay, so someone suggests that we test at 230 atmospheres and 400 degrees Celsius. Yeah, okay. Then you would expect to get a funny answer, which is supercritical fluid. Yep, okay. There are clear boundaries in these phases, so I would suggest, so somebody said, well, I tested 100 degrees and 1 atmosphere. Yeah, so at that point, what would you expect to get back at 1 atmosphere and 100 degrees Celsius? What answer should their code give you? Well, someone said steam. Is that right? So if you're exactly at this boundary, actually, either water or steam, either liquid or gas, could be an acceptable answer, because right on that boundary, it's not determined whether it's water or whether it's steam. But if you said at 99.5 degrees or at 100.5 degrees, well, then you could say for sure it should be water or it should be steam. So you might test a value right on the boundary between two things, but then you have to accept that there's more than one possible right answer. Just like if I ask you a question on a test, I mean, some of the questions I ask you only have one right answer, and some of them have more than one right answer, and I have to deal with that, and I have to be able to accept that. But you could go a little bit this way or a little bit that way. All right, what else? Is that it? Are we going to test those 2 points and call it a day? I guess your code must be right, so I'm going to cut you your big paycheck. No. So let's see. We've got -50 and 0.1 was a suggestion. Oh, sorry. No, I think Negative 50 comma 1. Okay, I see. So that's probably negative 50 degrees and 1 atmosphere. Yeah, so at that point, we would expect to have the answer ice. You might choose a bunch of different points, but you would want to choose. You would certainly not test every possible input of pressure and temperature because, like I said, if we have 2 to the 64 possible pressures and 2 to the 64 possible temperatures, that's a lot of tests to write. But you would probably want to write some tests that are spread out in the water area, in the ice area, and in the steam. And you'd probably be particularly interested in tests that lie right along these boundaries somewhere, the boundary between steam and ice, the boundary between ice and water, the boundary between water and steam. And you probably have a few tests that are either right on the boundary or right next to the boundary. So we can't possibly test exhaustively. We can't test every single possible input, but we could build up a pretty good test suite of inputs and the expected outputs that should go with them. And then we could just iterate through each of them and say, for each of these inputs, put in this input to the phase function, see what answer comes out, and see if the answer matches the expected answer. And that is mostly what my tests do when I write tests in the GradeScope AutoGrader framework. I give inputs and I say, call the student's function or pass these inputs to the student's script, see what answers come out, and then check. Okay, I expect that the output should have this string in it, and I expect it should have that string in it, and then I expect it should have that string in it, etc. So that's how my testing works, and it'd be fantastic for you to be thinking about how you can test your code. So here's an example. Let's say that you're going to write a function or a script or something. Now we're into functions, so let's think about it. You're going to write a Python function that I'm going to tell you a year, and you're going to tell me, is it a leap year or not? So if you have to do this kind of testing, or rather, let's reverse the roles. So I'm going to write the function that tells you, is it a leap year or not? And you're responsible for saying whether that code is correct. So are you just going to stare at the code and say, well, if I don't happen to see any errors, then I guess it must be correct? It's probably not a great approach. You may or may not be able to, this is a problem where it may be small enough that it could be possible to prove mathematical correctness under certain assumptions, but you haven't learned how to do that yet. That's something that you might get to in term 5, 6, or 7 or something. I think term 5 actually of computer engineering, if you happen to go that route using mathematical modeling languages like Daphne, but that's not something you've learned how to do yet, so you're probably going to write some tests. How many tests should you write, and what kinds of inputs should you pass in? Well, you're going to think about those kinds of boundaries. And so where are the cases, where are the sort of special cases and where are the common cases? And so I would suggest it'd be a really good thing to do as an exercise to think about, well, if you were going to write tests for this function, and if you were going to limit yourself to 10 or 20 tests, what years would you pass in and why? And then maybe compare that with each other. So correctness is kind of a funny concept. It would be nice if all of our code were correct, but we know there are probably ways in which it's not. But we would like it to be as correct as possible. And there are circumstances where we have a higher standard than just, if it's right, it's right, and if it's not, it's not. There are lots and lots of situations in which if your code is just a little bit wrong, it can cause complete programs to crash. Or in the context of engineering, where we build engineered systems that involve computing components, having software be incorrect could actually put people's safety at risk. So we have to care about these things a lot. The code that you're writing in this course is not so much in that category, but who knows? You may end up building systems that have embedded computing components where that software correctness is that important. So correctness is an important thing to think about. How do we know when something is right? Well, we can kind of have an intuitive sense of, yeah, that seems to be doing what I want, but really what we want to do is to have a specification so that we can then compare, does the specification match what we think is the right thing to happen. And if you can find an example where this is the wrong thing to happen and the specification doesn't capture it, then we can fix the specification. And then we can either prove the correspondence between our code and the specification, or more commonly, we can write tests from the specification and use the tests to check our code, which is also what is happening in assignments in this course. And I will try to get you an assignment 3 as soon as possible so that you can finish it and have time to do it, and we can have time to get all the 6 assignments in before the end of the semester. So that is it for today. So any other questions that people might have? Well, seeing none, I guess we'll say good day for now. And if you do have any questions, do feel free to send me an email or to drop by in my extra office hour that I'm having on Wednesday between 12 and 2. Bye for now.